Hello and welcome to Fouraye Academy. Today I'll be teaching stochastic calculus and financial mathematics. In the last section we explored the concept of Ito integrals. Now I want to quickly state some stuff about Ito's integrals, such as the expectation and the variance of the Ito integral. Now if you remember, the Ito integral is simply, the integral of a general process theta u by the Brownian motion. Now remember that this process is a martingale. Because this process is a martingale, when we take the expected value simply through iterated conditional, it'll give us I0, which will give us again 0. And when we take the variance of it, this is going to simply give us expected value of I squared t minus expected value of it. And since we know this is 0, and through the Ito's isometry formula, we know that this is 0 to t d squared u du. So simply the variance will be the Ito's isometry formula. It will be given through the Ito's isometry formula. Now for the main topic of this video, which I want to start at, is the concept of Ito's calculus. Specifically, the SDE form, or what we call the stochastic differential equation, or Ito's Ito double formula, or whatever it is. So let's look at this so-called stochastic differential equation. Now assume we have a function which generally we take as, of course, 1 over 2x squared, because when you take the derivative it'll just simply give us x, and when you take the second derivative it will give 1. So these are the assumptions for a function usually, since it makes our computation a lot easier. But in fact it applies over to all. So we have f of omega t, right? If you want to differentiate this based on a Brownian motion, how do you approach this? So this would be equal to f prime of omega t, and if we simply put this over here, we'll have our differential. But in fact, this is only true in classical calculus. In stochastic calculus, it appears that we have a drift term, or a term resulting from quadratic variation, which involves a second derivative. So what this term is of course f prime prime omega t dt. Now, how Ito visioned this is in the form of integrals. But before we get there, let's see actually what we've attained, right? What we attained here is that the differential is going to be equal to, now Brownian motion is of course not a differentiable function, so simply we'll just look at the differential, or the increment. As you see, this is the differential, and this is what we know as a stochastic differential equation, or an SDE. And when we say SDE form, we have something similar to this. So differential of something d omega t dt, that's the differential, or SDE form. So now we'll look at Ito's formula, which is an extensive version of this. But before this, let's look at this in terms of integrals. Now this can simply be boiled down to an Ito integral and a normal integral. So what we in fact get is that f of omega big T minus f of omega 0, which is equal to our differential, is going to be equal to the Ito integral f prime omega t d omega t and half of a normal integral dt. Now Ito has expanded this over onto over onto a function f of t omega t, right? And this simply shows that on the short term it has a risk-free value, but yeah. So ft omega t, how do you approach ft omega t? In this case, the differential of ft omega t will simply give us it will simply give us an Ito integral and a couple more simple integrals again. So first of all, we will of course have 0 to t f with respect to t omega t, big T, dt. So a normal integral. And then we'll have integral of 0 to t of fx t omega t d omega t. And x implies the other one, so plus, again, 1 over 2 integral of 0 to t fx x t omega t dt. And again. And over here, we assume that we had an f0 omega 0, which we threw over to the other side, and it became ft omega t minus said f0 omega 0, which results with the differential. Now, to further explain this, I want to showcase it in terms of summations. So we have f omega t minus f omega 0. Now let's say this, let's showcase this as a summation from j equals 0 to n minus 1. So f of tj plus 1 minus f of omega tj, right? Now this, according to, well, our thing, or in this case, this is simply equal to omega t, omega tj plus 1 minus omega tj. Now you could perhaps see where I'm getting to from here. Now remember our first, remember that first thing I said about the function being 1 over 2x squared and how it will make the computation a lot simpler. We'll see how it makes it a lot simpler in this case. So this is simply 1 and this is simply omega tj. So what we get is omega tj d omega t and 1 by the quadratic variation. So simply this can be expressed as the Ito integral, and this can be expressed as, well, the quadratic variation halved. And so the differential, we show that the differential can be expressed in terms of the Ito doble formula, which is, again, as I stated, given as such. Right. So then, yeah, that's pretty much it for the concept of SDEs and stochastic differential equations. In the next part, we'll be looking at Ito processes, and perhaps then we'll look at some more financial applications. But for now, that's it. Thank you for watching, and I hope you like and subscribe.